叫过来。
Okay, let's start. So let me deal with some issue that we left last time. So the last thing we did in last class was proving equivalent statement of axiom of choice. Oh no, after proving that, we did something about cardinality. Okay, and let me come back for this discussion of axiom of choice again. We want to end the section with ordering. Okay, last time we are in the midst of proving the statement 6 to 2, where if I know that, okay, if I know that every onto function I have a right inverse, can I produce a choice function or not? So last time I gave this naive onto function here. Maybe it's not onto. Okay, maybe it's not even well defined also, right? Like Ziqian said last time, because if you're gonna send x to something that contains x, maybe there are two things that contain x, right? Remember how we solved this problem? Assume that the x that come from different b are different, right? So Liongyan, I used Liongyan as an example last time, right? Liongyan as a son is different as a Liongyan as a student here. Reasonable, no? Reasonable, right? Because maybe you act differently, you have different character, in different places, right? You show different character. So we differentiate Leongyuan with the place is same. Okay. And there's another issue here thrown out by Tingyu after class. He said that this is well defined, right? Okay, even I make B well defined. Maybe this function itself is not onto, cannot be onto. Okay. Even if B here are all disjoint already, but here cannot be onto. Okay. So there's one example, it's very good here. So let's look at the example. Okay. So one example is let B be what? Let B be a set like 1, 2, right? So what is the union of everything here? B. What's the union of the set here? What do you get? Just 1 and 2. Means what? This means what? The core, the domain only have 2 things, but the core domain have 3 things. So you will never got a onto map here. Okay. So really you need you need the full strength of axiom 1 here. Okay, so meaning instead of looking this naive choice here, so what we do is we look at this G here. G from this C to B. So what's this C here? This C here is exactly what we consider in the when we prove when we're proving union of non-empty set to a disjoint union. Okay, but we only consider the set where the ordered pair such that X is in B. This is the only thing we consider here. Okay. We consider a specific C here. And then the claim here is this one will give us the give us this map here. You see, if I give a right inverse here, B only map to C, but we need to map it back to the union. Okay, we just need to compose with some clever choice, then it's enough. By the way, this is how to say, this is uploaded to the Moodle already. If you check before the class. Any question on this proof here? You know what's the issue and then how we solve it? You get what I said just now? Okay. Okay. Yeah. So this is about the proving of 6 to 2. Yeah, actually 6 to 1 is easier. But if you want to go from 6 to 2, then somehow you need to go through the method. You go through from 2 to 1. If you want to prove 6 to 1, right? The set you started with is already disjoint, so you don't need to do the extra job that make different, make X different. Okay, this is the comment I want to make. Okay, so before ending this, okay, before I continue, do you have a question on last lecture or assignment or not? So for the assignment, right, you can do references, okay, but you cannot copy answer. Okay, you need to paraphrase right in your own word. Okay, yeah. And then you need to cite if you get resources from where, right? And then if you're gonna use some theorem that I never proved before, you need to prove it inside your assignment. Okay. Yeah. And you are allowed to use whatever we prove it. Just use it after we prove it. You can just use it. Just say by this theorem, by that theorem. But if we never prove it and then you want to use it, you need to prove it yourself inside the assignment. Okay. Okay. If no question, then let's continue. So we want to end this chapter of axiom of choice. So lastly, we want to connect axiom of choice to well ordering. Okay, so to talk about well ordering, we have to start with relation. So I'll just quickly recall what is a relation. So what's a relation of the set? Actually, it's a set of ordered pair. Okay, so you just group two things together. So in discrete math, you should learn that set of ordered pairs are just relation. Relation are just set of ordered pairs. You don't need to tell me why, for example, if me and Ziqian form an ordered pairs, you don't need to tell me what's the real relation. Okay? You just need to tell me we are connected. That's all. Okay? So it's a set of ordered pairs. Okay. Of course, relation can be specified by maybe our H is the difference of 2. Okay, so we are related. Or difference of 3, we are related. But as long as you tell me we are related, that's all. Related by what? Not very important on this relation. Okay. And a relation is called an equivalence relation if it is reflexive, symmetric, and transitive. Okay. And two things are related. Okay. If you can put as an ordered pair, means what? Right. Means that the two things are equivalent. And then we will write A equivalent to B. Someone wants to come in as well. Okay. Hello, we have class change. Yeah. Okay. Yeah, A and B are equivalents. And then, so since A and B are equivalents, we can group them together, okay? And then group them as a set, which we call an equivalent class. Equivalent class. So inside equivalent class, we just only need to pick one representative is enough. Okay, we can find all the rest using this representative. So this idea permeates throughout the mathematics course, for example, discrete math, abstract algebra, right? Portion group, okay? We have this equivalence class ideas. Okay, representative. And then somehow we introduce this partition. Okay, partition of a set. So what is a partition of a set? How do you think about partition of set? Do you celebrate birthday or not? Do you celebrate birthday? You celebrate birthday? No. Okay, do you help people to celebrate birthday? Okay, got right. So you have a birthday cake. Right? You have a birthday cake. So you need to distribute a birthday cake. So when you cut the cake and then distribute all your birthday cake, so meaning you are like giving partition to the cake. Okay, so you cut your set into AIs, a set of AIs, a set of set, and then the intersection between two sets are empty. Right? Okay. And then the union of the AI is just your set. Okay, so why we introduce this partition here? So a very important thing about equivalence relation is if you have an equivalence relation on the set, you can form these equivalent classes. And these equivalent classes will partition your set. So meaning these equivalent classes won't have intersection. You cannot have intersection. If you have intersection, you should pull the element into your group. They should form one equivalence class, okay? Because they are equivalent. Okay? This is the property about equivalent relation. It is reflexive, symmetric, and transitive. So transitive is the one that you can put it in. Okay. And then next, how about I do something special on this equivalence relation? Instead of symmetric, I have anti-symmetric here. Okay, anti-symmetric here means what? If x is less than or equal to y is less than or equals to x, means what? X actually is equal to y, anti-symmetric. There's only one thing that can do this two things together. It is itself. Then this order, we will call it a partial order. Okay. This relation, we call it a partial order. Okay. Actually, you come across this partial order already. Which set have a partial order? Natural number. Let me think. Yeah, natural number is one. Or in more general, real numbers. Okay, real number has a partial order. And this, the set with partial order, we call poset. Poset. Yeah, poset. PO set. So partial ordering set. Poset. Okay. Nice English word. Sorry? Yeah. Three. Yeah, sure. Yes. You mean is three partial orders? Are three partial orders, right? This is your question. Are three partial orders? Cardinal. Okay, are you claiming that every tree is a partial order? Okay, so let me think. So let us think. So are three partial orders or not? So how is tree a relation first? So maybe if they are connected, then there's a relation between the two. And then maybe how to differentiate less than or equal to. So maybe using the hierarchy from top to bottom. Okay, depend on your convention. You can do it top to bottom, bottom to top also can. Okay, but choose one. Okay, let's say top to bottom. Okay, and then the top guy should be greater or equal to the less guy. Okay. Sorry? Yeah. Exactly. No. Wait. His diagram. Tree cannot be closed, right? His diagram can be closed. I mean, closed as in how to say closed. Okay, Hess diagram no need to be closed. Okay, as well. Okay, so yeah, Hess diagram is one kind of tree. Yeah. Okay, sure. Yeah. So yeah, partial order can be made into trees. I think so. Yeah. Hmm? Yeah. Many trees. You mean branches? Uh-huh. Branches between branches. What are you trying to say? Yeah. Yeah. It's a tree.
It's not one tree, many trees.
Ah, sure. Yeah, sure. So partial ordering here doesn't let me think. Yeah. So partial ordering here doesn't require you to actually there's a term for it. You don't need to compare every term. Not every two things are comparable. That's why it's a partial order. Partial is like not full order. Like why is it not full? Because I don't say that every two must be comparable. It's just that this two property happens, then I get this two thing. This is about itself, every element with itself. But I didn't say that every x and y I have to tell you whether they are related or not. Yeah, you can have a disconnected tree even. Yeah. Correct. Correct. Yeah. So I think combinatorics they call it a Hayes diagram. Yes. So does it make sense? Okay. Not everything's are comparable. Later we'll see what is the relation called if everything is comparable. Okay. Okay, next, since we have this order already, right? We can say some element is maximal. Okay, what's the maximal element? Such that an element x is maximal if for every y that is greater or equals to x, y equal to x. Meaning x is the top guy already. Everything that is greater than this top guy actually is itself. So this x is called maximum. And how we characterize maximum. How about maximum? Maximum. So you need to differentiate about maximum and maximum. Maximum or the greatest element is have to be greater than every guy inside your set. Okay. So meaning maximum element could have few of them. Okay? But maximum or the greatest element, greatest one, there's only one. Okay, there's only one. it have to be greater than everything else. Okay, maxima is just maybe you are maximum in your group. Maybe you are maximum in your group. But which one is maximum? You need to compare everything. Okay. Does it make sense? Okay. So we differentiate about this maxima and maximum. It is actually really close similar definition as the local maxima and the global maxima. So you can think of a maxima as a local maxima, but a maximum is a global one. You have to be greater than everything inside. Greater or equal to. Okay, so similarly, you can try and swap the order, okay, and define what is the minimum element, what is the least element, okay. In a higher mathematical phrase, we'll call this like a dual definition. Okay, we just swap the order here, and then we can define another dual definition. Okay, so you can try and define what is minimum and least element here. So yeah, so we come to this definition here. If everything are comparable, so either x less than y or y less than x, and then this subset we'll call it a chain. Okay, and then this chain we also call it a total order or linear order. Okay, you can put a total order here, or the order is actually linear. So that's why we call it a chain. So you can compare everything. So you can write down as a chain. And the order here, we call it total order or linear order. Okay. If everything can be comparable, then we can put as a chain, not tree anymore. It shrink down to a chain because everything we know which one is greater, which one is less. Okay. So we collapse the tree into branches, just one branch. This is what we call a total order or linear order. And then finally, we want to introduce well order. So well, why is it well? Well is like good. How good is it? Yeah, so what is a well ordering? So a linear order for which every non-empty subset of X has a least element is well ordered. So to be well ordered, you need to be, first of all, comparable for every two elements. You need to form a linear order first, and then no matter what non-empty subset you take, it must has you can find a least element. Okay. So for example, what set is well ordered? Natural numbers, right? So for example, if I take the natural number is 1. Okay, let's say we take our starting point. For example, what set is not well ordered? Real number is not well ordered. Can we go smaller? For example, integer also not well ordered because there's no least element for z. Yeah, very good. So more equivalent statement for axiom of choice. So axiom of choice is also equivalent to the Zermelo well ordering principle, which says that every set, actually you can put a well order on it. Just how we said Z is not well ordered, right? Well ordered with respect to the normal order, the less than. But can we put a well order on it? Can. Zermelo well ordering principle. Can you think of a way to put well orderedness on Z or not? Can you think of one? Who? Yeah? Z star? Z star. No, I don't want to change my set. I just want to change my order such that it is well ordered. I still take Z. Compare the absolute value. Compare the absolute value. Yeah. Makes sense? Yeah. Yeah, compare the absolute value. Yeah. Oh, sorry? Sorry?
In that way.
Yes, that's right. That's right. So this is equivalent to how I enumerate rational last time, right? Remember how I enumerate rational last time? Sorry. Okay,
Two ways. If we compare the
okay, okay, wait. So let's say we put I should say one less than equal to B if and only if A, the absolute of A is greater or equal to B. Like this, right? Okay, so you say that it will contradict the anti-symmetry, right? So if anti-symmetry means what? If okay, B greater or equal to A, then what? A must be equal to B. Okay, but in our case here, we can take A to be 2, for example, B to be minus 2, but A not equal to B. Right? But you can do some modification to this statement here. So what I want to say is use the enumeration that I showed you last time. How we enumerate Q? One way is to I can do 1, 0, 1, 2, 3 like this, right? So this is for a positive one. Maybe you can just put a -1 in between. Okay. Then this should be a well-ordering set. Okay. Okay. Yeah. Okay, so this is just one construction. I haven't proved to you why every set have a well-ordering. I just proved one construction that might work. And then third is a John's lemma. John's lemma says that a partially ordered set, okay, so meaning transitive, anti-symmetric, and reflexive set, in which any chain, okay, so you consider any subset that are everything inside that is comparable, has a upper bound that has upper bound, okay, actually has a maximum element. Okay, you can find a maximum element there for a chain that has an upper bound. And then Hausdorff maximal principle says that any partially ordered set contains a maximum element. So the theorem is these four things are equivalent. Okay. So to get one of them, you really need axiom of choice to hold. Otherwise, you don't know why it holds. Okay. So we won't prove this. Okay, we won't prove this. Don't worry, we won't prove this because the proof is quite involved. Okay, I've uploaded a document to I think week 2, right? About equivalent statement of axiom of choice. Inside there is just covering 3 of them. For our course, their proof are not very insightful, so we won't cover it. But I just to introduce you about this equivalent statement of axiom of choice. So if we want to do it rigorously, maybe we should start out a logic class. Okay, pure maths logic class. Why we can do axiom of choice. Okay, about semantic and so on. Okay, so this is axiom of choice, and then so one remark I want to make is maybe it's useful to check out Prof. Knox on the equivalent statement on well ordering on N and the principle of induction and principle of strong induction. This one might help with your assignment. Okay. Yeah, for the assignment, right? For my practice, I'm not sure what's your practice before, but you can do references, okay, and then please write down what references you take. Okay, if you have made external reference other than the lecture note or the textbook, and please don't copy answer. Write in your own word, paraphrase. Okay, if you're gonna use theorem, you can use all the theorem we have proven in class, or even like this, right? I said we didn't prove, but I already tell you it's true. So use it if you need. And if we don't do it in class, we don't prove it in class, then you need to prove it in person. Okay, so this is the practice for the assignment. Okay. Okay. All right. So we already end this part on axiom of choice. Then let's recall what we have done last time about cardinality. So how to talk about cardinality of a set? So we actually look at a function which is onto and one-to-one, which is bijective. Okay, meaning it is bijective. So two sets are equivalent or equinumerous, same amount of things, if I can find a bijection. And then we say that this equivalence of set is actually a equivalence relation. Okay, it's an equivalence relation. And then we said that a set is finite. Okay, if it is empty, nothing there, or it is equivalent to a set of 1 up to a set containing 1 up to n distinct object here. Okay, so you can find bijection with empty set, or you can find bijection with a set with n distinct elements. Otherwise, it is infinite. Okay, that's all. So this is a difference between finite and infinite. If you cannot find bijection between these two kind of set, then it is infinite. Then we have give some example. Let's say if you can find a bijection between natural number, then your set is called denumerable. Okay, meaning we can enumerate it. Again, we proved in the proposition below. We can enumerate the set, and if it is finite or denumerable, then it is countable. Okay, it is countable. So even though it is bijective with n, meaning there's infinitely many items, but it is still countable. So meaning I still can label it with 1, 2, 3, 4, 5, 6. This is what countable means. So yeah.
What if set S is completely then what if I have set S equinumerous is infinite, but there is equinumerous with something less than the hierarchy of n. Is it countable?
Wait, let me think. So what is the thing that is less than n? Huh? Yeah, what's the thing less than n? I think there's nothing between n and finite, I think. Pretty clear. It is pretty clear that there's nothing between I think it is pretty clear that there's nothing between the infinite n, infinite natural number with finite set. Because this is how we build out the natural number using this finite element. We keep adding the finite element. But the problem is about the infinity in natural number and the infinity in real numbers. Yeah. Actually, here we shouldn't have a problem because this infinity we build up by adding 1 to a finite set. Keep adding 1 to a finite set. Yeah, this is how we build n actually. Yeah. Yeah. So countable is a first step to infinity. Okay. First step to infinity. N is infinity, right? Already, but we could still call it countable because we can label using the bijection to label 1, 2, 3. Later you will see that there's an infinity that we cannot label anymore, okay, which we call uncountable. Later we will introduce this. So okay, so last time we did what? So last time we did that a set is denumerable if and only if we can enumerate the item, okay, using a sequence, exactly using the bijection with n, okay, because n has an order there. We can use the order on n. And then we prove that any denumerable set is infinite. Any denumerable set is infinite, okay. This is not immediate from the definition of denumerable because infinite, we define infinite to be not finite. Okay. But it doesn't say that any infinite set is denumerable. So don't take it wrong. So the order here is very important. I just say that any denumerable set is infinite. So this is the first step to infinity. And denumerable set also infinite. Okay, first step to infinity. Next proposition, any subset of countable set is countable. So If you have a subset of countable set, it is still countable. So countable have two possibilities. Either you are equivalent to, either you are finite, okay, equivalent to empty set or equivalent to a set of n disjoint elements, or you are denumerable. You are bijective with n. So this is the proof. So I mean, this statement is quite straightforward, but the important here is this proof. This proof is important. Okay, the way to prove it is important. How you build this countable argument, how you construct this countable argument is important. That is the thing you need to learn. Yeah. The idea shouldn't be hard. And then we prove that rational number is also denumerable. So this is quite important, right? We have n, okay, and then we go to z. So z is also denumerable. You can show it. But q, because z q, I mean z is in q, q is denumerable, so z should be denumerable as well. So we have proved this using a few ways. Okay, I draw some pattern for you. As long as you can give a max reasonable ordering. So, Jiayi, last time did you draw this like in the air? Yes. Okay, okay. So I managed to reconstruct your argument. Okay. Yeah, so this is his argument. So if you put your rational number, divide into using symmetry, right? But 0 is not belong to one of them, so you just put it in the middle, and then you create a path that can go through all the rational number. But I'm not sure how you write in words. I think you can, but maybe a bit. Yeah, sorry. Sorry. Minus 3 over 2 here. Yeah. That's right. Okay, okay. So I mean, you can do this. It's just that if you want to explain this in word, maybe a bit mouthful, but you can do it. This is what I'm just saying. So I mean, in pure maths, right? There are a lot of ways to prove one thing, but we prefer the shortest way, as short as possible, as simple as possible. Okay. But of course, in history, right? In history, when people come up with proof, maybe they will come up with proof of like 100 pages, 180 pages. First proof when it come out. But in the end, the proof will be simplified, okay, down to fewer pages. Okay. So it's very important that we solve problem intuitively, go straight to the point. Okay. We don't want to how to say, we try to avoid a lot of traffic. We try to avoid traffic. Yeah, this is what I would say. Okay, did we? Yeah, we proved this as well. Okay, so last thing we proved in the last lecture is if x is infinite, okay, s is infinity, so infinity meaning not finite only, just mean not finite. Then it contains a denumerable subset. That's all. I don't know what kind of infinity is it, but it will contain a denumerable subset. And then last time, remember that how we prove this, we're picking element from this set, right? Because it is not empty, we can pick one, and then we can keep picking it because otherwise it would be finite. So we can keep picking it until we form a denumerable enumeration here. Okay. Really, when we pick this guy, right, we have made an infinite choice here. So really, we have to use the axiom of choice here. Okay. We have made an infinite any choice here. Okay. So actually, we use this axiom of choice when we make this choice. Okay. That's why I have a memes in at the start of the class. So if we want to make an infinite choice on the vector space, basis of the vector space, right? We somehow require axiom of choice. Yeah. Okay. Okay, I think we should start new stuff. Okay, let's start new stuff. So let me bring this in. Copy. Okay, so one corollary from this theorem here is the cardinality, the cardinality of x, okay, should be greater than the denominator subset. Okay, we haven't introduced this concept yet. So later, let me introduce first and then we will talk again. Sure. Let's see what else we can do now. Okay, so let's do something different first. Then we will come back and discuss this. So let's come back later. Until now, I haven't defined cardinality yet. I just talk about bidirection equivalences. Okay. Later, when we talk about cardinality, and then we will come back. So what else should we do? Let me see. Okay, let's do this one first. So proposition. So a countable union of a countable set is countable. Does it make sense? A countable union of a countable set is countable. You don't really increase much. Actually, you don't. Actually, you don't have increment. Do you think there's a lot of things here or not? This set is already countable. Countable means what? Either finite or equivalent to n. Okay, let's say equivalent to n. And then you take number of equivalent to n of them. Shouldn't it multiply up? Propositions here say no, it's just countable again. Okay, so this is a concept of infinity. Yeah, countable. So how to write this in word? So if A1, A2 is a sequence of countable set, countable union means you can take up to like 1 up to infinity. AI is also countable. If you want to take just a finite union, right, means what? Maybe you can set the rest of the AI to be empty set. Sense? Okay, so we phrase it as a most general way here. Okay? If you want to set it as a finite union, right? So you just set the thing behind as an empty set. So you know how to prove this? Any idea? Sorry. Yeah. Countable, right? I equals to 1 to infinity. 1 and 1, 2, 3, 4, 5, 6, 7. Right. Right. Yeah. Yeah, countable. So this I here live in natural number. Is what you meant, right? Yeah. This is implied by this 1 to infinity. Because if we label with real number, we won't write like this. We won't say like 1 to infinity if it is real. We will like specify it as a real because there's no ordering there. I mean, there is ordering there, but the normal order is not well ordered. Okay, this is fine. Okay, so okay, so any idea on how to prove this? List the element, right? Is similar to the rational number, right? So you just list A1, A2, A3, A4, and then you do the whatever pattern you want to do. Okay. Can or not? Can I skip the proof? Can I? You know what I say? If you know what I say, please go back and write it out. Okay, please go back and write it out. Okay, make sure you really know it. Okay, if you start and then you should come back and ask me. But the idea is the same as the rational number. Yes. Can you prove by induction? You can. But you can, yeah, you can, because now is yeah. But when you do that, right? When you do that, let me think. Yeah, you can, yeah, you can, you can use induction because can you, sorry, sorry. Wait, let me think. Can you use induction? Wait, let me think. No. This is not about induction, right? Because this is 1 up to infinity. Induction is like 1 up to n, right? Pn. Your Pn is what? Your Pn has a finite n, right? This one is infinite. I'm proving more general statement. I'm proving more general statement. Yeah. So I'll just prove it as one go. It's okay. Yeah. Yeah. Because I'm go to infinity already. It's not a finite n. Okay. Okay. So this is okay. This is all good. Next. Next proposition is also interesting. Let's say I have a two family of mutually disjoint set. Okay. Okay, now this I is any index set. I don't care whether it's infinite or not. But one thing I require is this set of AI and BI are mutually disjoint. Okay, meaning BI, BJ intersection is empty and AI, AJ intersection is empty as well. In that set, I don't care. Let's say, okay, let's say every AI and BI, there's a bijection between them. Then I can form a bijection between the union of AI and BI. Then maybe think about it. Is this clear or not? How to form this bijection? How do you define? So I give you some bijection. For all I give you a bijection. Can you form a bijection between the union or not? How? Sorry? Say again? What do you say? What are you saying?
Bijection.
Bijection from here to here. Yeah, bijection from here to where? N? No, I don't know what are AI, BI. I don't know what size are they. I don't know the size of I as well. But can I form a bijection between the union? Which one? No. This is no. You mean this is equal to N? Why? Uh-huh. No. Because I'm not using the previous proposition. I don't have size on AI and BI, and I don't have size on I. What I know is AI and BI, there's a bijection. Every two things here has a bijection. I mean, with the same I, okay? And then I can construct bijection between the union. Union means what? I collect all the AI together. On the right hand side, I collect all the BI together. But between AI and BI, I know the bijection. What can I do? I compose all the bijection, right? How do I write this down? So one naive way to do it is since AI is equal to BI, right? There is a bijection from AI to BI. So how to make a bijection? Okay. So one very obvious way you can define bijection is you will send X to Fi of X for every X in AI and for every I. Okay, if the X is in AI, then I just use the bijection before, send it to BI. The claim here is this map is actually 1-to-1 and onto. You need to prove it. And this will require the mutually disjoint thing to work. Okay, so prove it yourself. Prove that this is proof that F is 1-to-1 and onto. Actually, one of them is pretty easy to see. Onto is pretty easy to see. Okay, but 1-to-1 require the mutually disjoint property. Okay, yeah. Do we require axiom of choice here? Not quite. Not quite. Let me think. Do we need an axiom of choice here? No. We just use property of onto. We just use property of onto because onto will give you the pre-image. Axiom of choice is when you want to build a right inverse function. You just want to pick one, specifically one, but here is just existence that exists. Ah,
Yeah.
Yeah.
Find the F. We
Yeah.
find on the single F.
yeah.
How can we pick out the single element X from? Wait,
Just by the onto-ness of Fi. Fi is onto if there is a pre-image such that it maps to the image. Yeah. Axiom of choice, you need it to build a right inverse function. Yeah. But here you just need an existence of pre-image. Okay, try and prove this. Can I rely on you to try and yourself? Try and prove that this map is 1-to-1 onto. I'll put it inside my note later. Okay. Okay, good. Let's go on. Let's finish up to n and 0, 1 is not equivalent, then we will take a break. So next proposition is about product of set. So if you take n product of countable set, it is still countable. Where does this apply? Do you remember where does this apply? Where do you see this thing? This kind of thing? Or actually not yet. Actually not yet. Never mind. So I wanted to say about R, but R is not countable. But later we'll see it. So how to prove this? So this statement is about n, right? So we can prove by induction here. Where this statement can be proved by induction. Well, this statement can be proved by induction because the statement is about n, have to true for all n, right? So it can be proved by induction on n. So what's the base case? Base case is 1, right? But A1 is by definition countable. Okay. So how about AK plus 1? Okay, so how about, okay, not AK plus 1. So let's say, so assume A1 up to AN is countable. Okay, so we want to show that A1 cross cross out to AN cross AN plus 1 is also countable. Okay, so how? Any idea? Actually, there are a few ways to do this. Maybe I show you one of the way. There are a few ways to do probably, but let me show you one way. So since AN plus 1 is countable, something is countable means what? You can enumerate it. Okay, let's enumerate it. So let's say x1, x2, okay? You can enumerate it. Then we can define a new thing called BI. Right, so what's BI here? So A1 cross out to AN cross one element set X1 Si. Okay. So in this case, what is the product set of A1 up to AN plus 1? This is the union, right? Union of BI. Okay. Then I can use the proposition just now. Countable union of countable set is countable. Okay. Because countable union of countable set, this set is countable, right? Because by inductive hypothesis here, this set is countable. Here, doesn't matter, right? I just put one thing there already, only. So it's one thing with the countable thing. So it's countable. And I add countable union of countable set is countable. Okay. But you can come up with other proof if you want, if you don't want to use proposition before. Okay. Yeah. In this chapter, it's quite free. As long as you can produce a bijection, then you are fine. Yeah. As long as you can produce a bijection, you are fine. All right. Let's see. Let's see. Are you guys still okay or not? Can we go for one theorem and then we take a break? You guys still okay? Okay, let's go to one theorem. Let's see why we need to go a further infinity here. So we want to show that the natural number is actually not equivalent to R, or actually it's not equivalent to 0 to 1. Last time we have shown equivalent between R and 0, 1, right? Okay. So let's see why n is not equivalent to 0, 1. Have you guys seen the proof before? Yes, in discrete math. Oh, okay. Then we go faster a bit. So let me see. Actually, there are two proofs I want to do. So what kind of proof you have seen? Cantor diagonalization. Okay, so you use the decimal expansion, right? So you use the decimal expansion. Let's say we can order it, right? Yeah. Let's say we can order. Let's say we can. So let's quickly go through what is the Cantor diagonalization property. So let's say we can enumerate everything inside 0 and 1. Okay. Let's say we can enumerate it. Right. Let's say we can enumerate it using the decimal expansion. Okay. How we construct the contradiction here? How we construct contradiction here? Make another number. So what number are you gonna make? So we take the A11 term, A22 term, in particular the AJJ term, right? Okay, and then we form a new number which is not equal to any number in the list, because this is by construction. Okay. Okay. Since everyone happy about this, then we are fine. But you need to make sure, there's one thing you want to make sure is there's a problem in decimal expansion, right? Like, for example, 0.100000000 is equal to 0.099999999. So you need to fix your convention. Either you want to pick this convention or you want to pick this convention. Otherwise, you will get two same numbers with different expression, with different decimal expansion. Okay, does it make sense or not? Okay, so you need to pick convention. Okay, pick convention. Otherwise, you will have different decimal expansion but represent the same number. Okay, so you need to, in your proof state, I want to pick this, or I want to pick this. Okay. Otherwise, you have you won't construct this contradiction proof. Okay, if you have seen this proof, have you seen a proof using completeness of R? Oh. Okay, let's do this. So let me show you a second proof for this. So this one is the Cantor diagonalization argument. Okay, so let me use completeness of R to prove you. So, so suppose AN is a sequence of real number, and let's say we can order them, right? We form a sequence of real numbers. Yeah, let's say we have a sequence of real numbers. What we want to show is what? To show that they are not equivalents means what? We can find an element in the interval 0 and 1 such that what? Yes, it's not equal to any terms inside the sequence. Then we are good. That means we cannot form a pure sequence using real numbers. Okay, so how we do this? How we find this R? So we have a sequence. How do we find this R? Okay. So we construct, let X1 be a closed sub-interval of 0, 1, such that what? Such that A1 is not in I1. Okay. Because we want to find something that is not in the interval, right? So we throw away A1 first. Okay, we find a closed sub-interval such that A1 is not in there. And then what I do next? I'm going to do this inductively. And then I'm going to pick a smaller interval again, such that what? A2 is not inside my new interval. Because I want to find something that is not equal to all of the terms. So I keep doing this. So inductively, what do I get? I get a sequence of interval. Right? I get a sequence of interval. And this sequence of interval satisfy what? What kind of property? It is getting smaller and smaller. Okay? It is getting smaller and smaller. So how do we write this interval here? So let's write the interval with endpoint. Let's say alpha n and beta n. Okay, left and right endpoint. And with this subset inclusion, right, you can see a interval nesting. Like alpha n greater or equal to alpha n plus 1, strictly greater than beta n plus 1, less than beta n. Okay, make sense? Can I? Okay, the middle here is strict because we have a proper interval. In particular, what? Anyone recognize here a MA trait here? You have this kind of inequality. What kind of trait you can apply here? Alpha n is a bounded above sequence, and beta n is a bounded below sequence. So you have a bounded above and bounded below sequence in real. Means what? Supremum and infimum exist, right? So you can find what is the sup of alpha n and inf of beta n. Why exists? Because we live in the world of reals. So reals is complete. Okay. Furthermore, we claim that this alpha and beta is the interval that we can find R. Okay. It is clear that alpha and beta is in In such that for every n, and this interval will exclude exclude all the an. This is by construction. So you just pick anything inside this closed interval alpha beta. Yes. Why does it do not equal to? I think you need to derive from here. The strict inequality here. Yeah. Let me think. Yeah, so strict doesn't apply to the equality, right? Because if like you have an open interval 0 to 1, right? But the increment of 0 to 1 open interval is still 0. Yeah. I think you are right. Even if it is equal, then that's the number you want. Yeah, if it is equal, then this interval is a singleton. And that singleton is the number you want. Yeah, I think you're right. Okay, no, this is using the completeness axiom. But I think this proof actually is quite intuitive, right? If you have an an like this, right? So I mean, you can simply pick this interval like that, maybe. Right? But this proof, right, maybe deal with more complicated an. For example, what? For example, this an will be like a1 here, a2 here. Maybe it alternates alternate a lot. Yeah. So to avoid, yeah. So to talk about this, how you find things inside, then you need to use this more sophisticated way to describe it. Find a closed interval such that an is not in there. Okay. And then the final part of this statement, this argument is we use the completeness of R to really pin down the interval we want. Yeah. We use the completeness of R to pin down the interval we want. Yeah. Because if you do it inductively, you do it infinitely many times, where it stop? Yeah, it stop where the completeness of R will give you the supplement and infinite. Sense? Okay. Okay. Alright. Yeah. Another way to think about this, just now I think of a interesting way. So maybe if you like you are from a bird eyes. You know what's a bird eyes mean? Bird eyes and frog eyes. Yeah, you look up from down. You also you see everything. So let's say I give you some sequence like this. Surely it is easy to pick an interval that doesn't contain everything, right? So you just pick something in between two terms in the sequence. But let's say you are a frog eyes, meaning you don't know what's all the term inside the sequence. Okay. Say if I pick this interval here, and then you say here there's an an again. So how are you gonna pick? So maybe I'm gonna pick this one, but here there's gonna an again. So you're gonna pick another interval that avoid all these an. So this is what we did in the proof. Okay, so you are like a frog eyes. Yeah. So this is typically what not typically but one of the way we do the proof. Okay. Sometimes we can straight away see everything, but sometimes we need to do things step by step. Okay, but this one is inductively we need to step by step. Okay, any question about this? So you see, this theorem is very important. N is an infinity set, R is an infinity set, they are not the same. So we need to create new thing for these two. Okay, so let's come back after break. So let's come back 220. We will associate name to them. A 问题关于什么？
我们花了差不多2个上这个教出来什么？但其实感觉好像在我看好像就是在一个 set 上面它的关于它的，还有就是它的现在的确关于它的那个叫 inversion。inverse 所以它其实很创新，它还有其他意义嘛？那这个 inverse 是干嘛？
那刚才我不是说 sequence segment
对，就跟其他3个
可以 order 全部都是一样，对，还有那些哦，
其实我蛮恐惧的，就所以我看这个访讯看到就其实我也
哦
有点乱，我不懂它到底要干嘛。
，Excel 说你学到吗？
可能来比如说
变得根本。
就是来讲 set 啊 set 的 definition 啊，它到底的那个用处，可是老师他可能学习他的就是为什么一开始他会这样子设跟他的定义是什么？我需要的 definition 就是他为什么这个时候？因为我们一上来就是不管微微动，有些人他怎么来。是不是这不一样？是一个选择性的一个问题。
对对对，他选择性的，Yeah，我想一下，等等。所以如果你 buy 不 buy，我说这个是种 choice for 你来做一个infinite choices，就是说凭什么我可以从一堆东西里面，凭什么我可以一直从一堆里面一堆东西里面选一个东西出来，要一直做哦，一直从一堆的东西里面选一个东西，为什么我可以这么做？
这是康吗？康可以看范围的，但是如果这个是我刚刚证明的啊，它的 Cardinal R 的序符和词典的可以做的，这么多词典我可以。
可能你要 induction 的
我这个就到就是你这样子想，就是如果那个东西很你的那个代题里面看不出，但是那是很美的话，你有一个方法可以选。
而且在 real number 上有办法选。
其实你可以选，我看到你还可以选，但是如果那个几何变得很复杂，你有没有一种很统一的方法把一个东西给选出来？
所以它的 Excel 就是你没有一个统一的方法，但是你可以写，
是可以啊，但是就是你老是讲可以啊，但是
它是跟你讲 able to control
对
able 把不呀，但没有它跟
讲
它就推不出，
不是一个固定的，
不是固定，
对啊，
不是一个固定的方法。
好像你懂，那袋里面有东西啊，你可以选啊，但是在数学上这个东西是
他们并完成后面的啥，就你给带一个方圈，在方圈里面是你，然后就是可能可以做到它，
数学上很多都是
对，所以
但是
对，所以你看它的 phrase 在这些地方呢，它都是，如果回去一下那个，所以它的 phrase 都是 that exist 罢了的，它没有告诉你 that is a unique 呢还是什么这样，就是你能够做都，但是给我看看，
就是你每一个就是一直都有很多种选的不同。
对，actually 可以有很多种不同，不是 right inverse，right inverse 你的 pre map 里面有很多东西的，其实你选哪一个你都可以变成。
我可以，可是肯定是depends 还是就是你就想到，如果你可能讲，OK， 我这个能够配一个东西给他，你如果是这个现实生活中你的代都没选出，哦，没有选出来，但是那粒球为什么要选是那粒球？为什么要选其他粒球？
其实都可以，
对啊，
其实都可以，
这都可以，但就是因为这都可以，所以你就不懂要怎么写出来
对，
他们有一个很规划的那个需要，所以叫 AOC
对，这个字我们叫 canonical， 没有一个 canonical way 去做。
fix 哪个 fix， 或者是 canonical 大家都有，
就是没有一个字对，没有一个
自然的选择
啊，对，自然，对，自然可能没有一个自然。
因为那几何可以很复杂，对。
X 是方圈
啊，对，
是 S 什么？就是说自己选一个方圈，它有了就可以就可以了。
对，
你知道你就可以了哦。
啊，对，
就是很可惜那种，
我知道它可以写成这样子，我知道它可以有
啊，对，
这些地，我知道它可以变成白的，
对，
是那个方圈。
但是重要的是这个 X 告诉你它有
啊，但是
如果你没有，你很多事情都做不了的，因为我 prove 了 equivalence 嘛。你如果这一个都做不出来啊，你这个也不用做了，
为什么不用写
啊？不用做了，所以呀，
他就跟你讲原因的，
就很可惜，这种人更不出来，就是还会把它推
他无法从一个比它更 primitive 的一个 axiom， 如果你要的话，可能你要去，有可能啊，你可能再去找一个更 foundation 的一 set axiom， 可以把这个东西推出来。目前呢 ，axiomatic set theory 还是推不出。
除非你拿
咱们咯 ，Frank 也是 prove 不出，都 prove 不出，
除非你这样子，
也是 prove 不出来。
对啊，
也是 independent，这个 axiom 是 independent of 现在所有的 set。
很多人都已经拿那个 set theory 一直拿线子了，对吧？这种才是，
哎呀，
拿
目前也没有东西可以把它推出来，所以我们还是把它看成一个 axiom， 除非有一个更 foundation 的 axiom 可以把它推出来。
就是很多东西你知道你可以选，但是你写不出来。
啊，上帝给你个选择是，我们证明不出来。神让你做选择。
大家都打选，那个就是
Yeah， 很 interesting 啊，这个 axiom 觉得 ，Yeah， 可以多想一下。Yeah， 不用了，我们都 prove 一个分。
然后按你写出来。
啊，你要写也是可以，但是我们只要
出来肯定很多是全部。
没事，你有第7个啊？
没有，对，他是不喜欢。
可以啊，你就 label， 我有 label。
你可以写新的，只要你的大是。是啊。
对，也是啊，很多啊，这个
很多，因为 AOC 是你可以放在很多个领域。
对。
但是你要选，基本上这个要选方式。
对。Yes， 因为啊 ，even in different reference 啊 ，depend on context 啊，他介绍的 axiom of choice 可能一本书是介绍1，另外一本书可能介绍3，另外一本书可能介绍2，看起来很不一样，但是还是一个。
这种在选的东西，那个东西是什么？
你要的结果不一样，你做选择不一样哦。
你要的结果不一样，你做的选择不一样。或者说你做的选择在不一样的情境里哦，
他会做不一样的事情，
他选他东西不一样。
当然他选的东西不一样，但是是说来，来讲这个东西，
他选的方法是方法，
你选不一样的，做出来
原理
原理是
选的原理是一样，
有讲选的原理，因为他没有选的原理。
OK， 对，你们讲的都对，其实因为你们讲的不在同一个频道。因为什么？你知道为什么吗？因为你是讨论怎样去选，但是我们只是说选的原理是一样的。对吗 ？OK 啊 ，Yeah，对怎么说哈？有人在讲如果 people say God is infinite 嘛。但是你看我们的 word 应该是 denumerable， 所以我们可以拿 denumerable 的东西去解释所有的东西。我们解释得完所有的东西，因为如果我们要解释的话，我们是用语言嘛，语言是 denumerable 嘛，对吧 ？A B C D E F G 才26嘛，26你再乘26，再乘26，看我们是 proof 了没？还是 countable 啊？但是这个世界要懂的东西是 infinite many， 我们懂得完吗？ Okay, so we should think about this. Okay, keep this in our mind. So yeah, so let's come back. Wait, where am I? Okay, so just now we end with natural number is not equivalent to the open interval 0 to 1, which is equivalent to R, meaning N and R are not equivalent. Okay. So corollary, N is not equivalent to R. If it is equivalent, means what? If it is equivalent, means what? Then N is equivalent to 0 to 1, which is a contradiction. Okay. Okay, so we need to define a new infinity now. Okay, so we will say that a set. Well, where am I? I read a stupid thing here. A set is uncountable if it is not countable. Okay, I think it's correct. So a set is uncountable if it is not. Am I giving the right definition? A set is uncountable if it is not countable. Let's say this is our definition. And then let me think. Am I correct or not? So correct. I didn't think carefully when I write this down. A set is uncountable if it is not countable. So meaning it could be R and then something greater than R. Let's say we take this definition as our uncountable. And a set is equivalent to R. We say that it has a cardinality C. Okay, then we will introduce what is the cardinality means. Okay, C here means continuum. Okay, continuum. Later we will make a bit more precise what does this continuum idea doing here. So now we really define what is a cardinality or a cardinal number. So to each set, okay, we can associate a symbol, which we call the cardinal number. Okay, cardinal number. Or is the cardinality simply put as a cardinality of X? Okay, so I denote it as absolute value of S. Sometimes you will see book put like double bar, the notes I put on the Moodle. I'll prefer absolute of X. Then we will say that the absolute of X equal to absolute of T if and only if there's a bijection between them. Okay. So what are these numbers? Yeah. So if my set is empty set, that's meaning there's a bijection. If we have a bijection with X, let's say we have bijection with X with empty set, then the cardinality of this set is just 0. Okay. And let's say, okay, you have a bijection with n disjoint element, then the cardinality is just n. Okay. And if you have bijection with n, then we will say that your cardinality is D, denumerable. Okay, D. Or sometimes you will see omega, alpha and omega. Somehow they think that is the end already. Actually, it's not. You know, omega is what? Is the last alphabet in the Greek. So they thought finish already, omega. Actually, it's not. It's just the start of infinity. Okay, yeah. So in other words, there's another notation called the alpha. I love 0. Okay, I love 0. Yeah. I love 0. Yeah. ALEPH, yeah. Okay, actually, you are just the start of infinity, not the end. And then the next infinity you see is exactly this real number. We call it continuum. Okay, sometimes I think people write here as a LF1. and then you should expect there's more infinity. There's a lot of infinity. Actually, if you come to the last seminar by someone outside from Amsterdam, he talked about a lot of kind of infinity in his seminar talk. Okay. Now sorry. Why is it LF1? Huh? Okay.
So it's
Yeah.
we have to
We didn't prove. They just defined it. Yeah, we didn't prove. And they didn't prove. I mean, all of us haven't proved. Yeah, all of us haven't proved. So why is it the next one we haven't proved? We don't know. Actually, we just call it. Yeah, we never prove it. So we just take it as a. Oh, okay. So the problem here is why is this the next infinity? Right? Yeah. So actually, this is an unproved statement, and they call it the continuum hypothesis. So there's no cardinality between the numerable and this real number C. Yeah. Huh?
Is equivalent to just
Yeah. Is this the assignment question? This is the assignment question. Huh? Where is it due? This? You sure? Friday, Friday, right? I think Friday. Yeah, Friday. Always we make it in the weekday. Weekend is haram. Weekday is cannot put. Okay, so later we will comment on this continuum hypothesis again. Okay, later we will comment on this. All right. Talk about this already. Okay, and then next you can see this set. This set is quite resemble what number does. Okay, let me show you another definition. Suppose we have two sets. Okay, we will write the cardinal of x is less than or equal to cardinality of t if S is equivalent to something inside T. Okay, so meaning there's a injection into T. Make sense? Okay, so there's some subset M. And if we know that there's an injection from S to T and the two sets have different cardinality, then we can say that we can safely write that the cardinality of X is strictly less than the cardinality of T. Okay. Then the next proposition is we want to show that 0 is less than 1, less than 2, less than 3, less than D, and then D is less than C. Any idea how to do this? Maybe talk about the finite one first, right? Can you see injection or not? Along here. Can you see injection? Can you see injection or not? How to prove this? This is number, right? This is number. Okay. So definition here, we have this inequality of number by set. Okay. So can you think of some set that realize this inequality here? For example, my claim is I think it is pretty easy to see this one because you can have an injection from fewer things to more things, right? For example, say A1 goes to A1, A2. What can you do? What's the injection you can do? You can send A1 to A1 or you can send A1 to A2. This is the freedom you have. And then just now we proved that infinite set have a denumerable subset. So you can map into a denumerable subset of your infinite set. Okay. But the problem here is we need to deduce that the equal signs won't hold in each case. Make sense? Okay. So I think here is pretty obvious, right? For example, 0, can 0 equal to 1 or not? Cannot, right? Because empty set is not equal to the singleton set. Because the element in the singleton set is not in the empty set. Okay. And then you can use induction to prove the rest. Okay. And then what else? What else you need to show? So you also need to show that for every n in n is not equal to d. Right? Does this make sense? Why? If d equals to sums n means what? N is finite. So contradiction. N is not finite, right? That's n is not finite. Try and write down the full argument for yourself, for the sake of yourself. Okay. And then can we argue that d not equal to c? I think last time we did it already, right? Because n is not equivalent to r. Yeah, and then prove by, or prove. So here is 1, here is 2, here is 3. So prove by induction that 1 is not equal to 2 equal to 3. Sure. Okay. Does that make sense? Yeah. So far, so good. Okay. 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 Let's see what thing we can do. Okay, let's do one thing here. So we have this terminology now. So let's come back to this theorem that we have proven last week, the last theorem. So if S is infinity, S contains a denumerable subset. What can you say about the cardinality of X? Yeah. Bigger equal to D. Okay, good, very good. So this is just a corollary that it is bigger equal to D because you can find a denumerable subset inside your infinite set. And then let's prove one more proposition here. So let's prove one proposition here. Let A be an infinite set, is just not finite, yeah. And B a countable set. Okay. Can you guess what is the cardinality of A union B? Is A. That is A. Is A. And how to prove this? How are you going to prove this? Yeah. Sorry.
So the unit from A to A to B.
Okay, we want to form bijection, is it? So how do you form bijection? So let's prove it. So B is countable, so you want to list it down, is it? So let's list it. Can you list it? Okay, let's list it. So how to form the bijection? You mean A union xi like this? Is this what you say? You want to continue or you want to think about it? Try and think about it again. Okay. So what can we do here? A is infinite, right? So we can find what? We can find a enumerable subset inside it. Right or not? Just now we proved it. Not just now, but last time. Set. Let's call it AI inside A. So since B is countable, B take out everything in A is still countable. Countable means what? Either finite or enumerable. So you have a enumeration, and then you just take out things that is in A. Again, still enumerable. Then what can I do? Yeah. Then consider this one. Consider A1 union B take out A. This set in particular, it is countable because countable of countable set is countable. Okay. Plus what? Plus actually A1 is equivalent to A1 union B slash A. Because A1 is countable also. This is by our construction, how we pick A1. So can we do something clever a bit? Then I can split A to be something that is countable and some other things. I can split like this. And then I can form equivalence between A take out A1 union with A1 union B take out A. What is this thing? A take out A1 union with A1 union with B take out A. What is this thing? Huh? A union B. I take away A1, I put it back. I take away A, I put it back. Right? So I get A union B. So I form a bijection between A and A union B. Okay, but yeah. Okay. So I have a bijection between A and A union B, though. That means their cardinality is the same. That's a very good application of this example here. Which is what? Irrational and rational. Rational are enumerable, are countable, right? So let me put here. So a very good example here is R take away rational, put it back is real. Irrational plus rational is real. Okay. And then what do I want to do here? So A here. So A, this is set to be A. This is set to be B. Right. So what do I get? Irrational is as many as the rational. that make sense? A is irrational, B is rational, A is irrational, A union B become real. But we know what's the size of real. So there are as many irrational and real. But rational is just countably many. Does it make sense? So actually the thing that make up the real numbers, most of them is irrational. But how many irrational numbers are useful to us? Pi, E, well, square root of maybe. What else? Not much. We only have these three classes. So do we have? Yeah. So they are more irrational for you to discover than rational. Yeah. Does it make sense? We should have a few on irrational number then. How many irrational number you cannot play with? Right. So yeah. We should have a study on irrational number. There are a lot of more irrational number than rational number. Yeah. Because you know why? You know why? Last time Greek thought that in particular the Pythagoras, they thought that rational can explain everything in this world, right? Everything work with rational number. But turns out that you need pi. You need square root 2. Square root 2 is the hypotenuse of the right angle triangle that have a side 2 and 1. 1, 1, yeah. 1, 1. Right? So they are more irrational in this world. Okay, so this is about this. And I think in the tutorial, I asked you to construct, if I'm not wrong, I forgot already, but I asked you to construct a bijection directly from irrational to real. If I'm not wrong. If I'm wrong, please do the exercise. Yeah. Can you produce a bijection without using this theorem here? Can you produce a bijection from irrational to real numbers? Okay, can you straight away produce a bijection? Okay. It's a bit like the Hubert, if you know the Hubert Hotel. Okay, so you need to push something to the back, push something to the back, push something to the back. But you can keep doing this because it's infinitely many of them. So you can keep pushing things back. Yeah. So if we have a logic course, right? Hubert Hotel is one of the things they discuss. Okay. Let's see. On next. Okay. Let's. Should we do this or not? Okay. Let's write down the statement first. Theorem or proposition. Suppose A is non-empty. Then for any set B, there exists an onto map from B to A if and only if the cardinality of A is less than equal to B. Do you think that this is obvious or not? Is this obvious? Is this obvious or not? You have an onto map means what? Everything in the A, you have a pre-match. So it must be the case that B have more things than A. Okay, but the other thing is if you have this inequality here, you can come up with a onto map. Okay. So should we quickly prove this? Huh? Let's quickly prove this. What time is it now? Let me think. 1, 2, 3. Are you guys in rush? I mean, do you guys need to leave after 3? No. If you want to leave, you leave. It's okay. That's fine. I want to know how many can stay only. All of you have to leave. Is it? No, just let me know. It's okay. It's fine. You cannot. Okay, how many of you need to leave after 3? 1, just you. Okay. Then maybe I drag until 3:30. Can or not? I want to finish set theory. Next class I want to start matrix wave. Okay. Okay, if you want to leave, you can leave because I got recording. You can push back. Yeah. I just don't want that I only the one that stay. Okay. So if that case, then we prove this then. So let's prove this. Okay. So I'll prove this. So one direction. Let's pick a direction. Let's say from left to right. Okay. So we want to show that A is less than or equal to B. So by definition, is what? A is injected into a subset of B. So I have to find a injection. Okay, how to find this injection? There's an onto map here. How to find injection? There's an onto map. By set of choice, I can find what? Yes, I can find a right inverse from A to B. From A to B such that, okay, let me write down from A to B such that GFX equals to X for all X in A. The claim now is this map is 1-to-1. Is it clear? Why is it 1-to-1? Why clear? You can use checking, but I think this is the assignment question, right? Yeah, if and only if it is 1-to-1. Am I correct? Identity, and also you need to be careful with left or right, because one of the order is onto one of the order is 1-to-1. Okay. Then I think by the assignment question, F is 1-to-1. Or like Gary said, just go and check it. It should be 1-to-1. And you just check it. Okay, so this is one direction. So one direction you require action of choice. How about the other direction? Since we know that A has less thing than B, or there's a bijection, or there's an injection from A to B, can we define an onto map or not? How do we define an onto map? So, I mean, this F is injective, right? So I know where A goes to B. But how about something that is not approachable by A? What do I do to them? Huh? Arbitrary. I just make it arbitrary. So what do I mean by that? So given any y in B, I just define y get sent back to x if fx equals to y, and I just send the rest to something else. Okay, if there's no such as no such. Okay, where A is an element in A. Why can I do this? This is exactly why I have to assume A is non-empty. Okay, so since A is non-empty, why I can just simply pick anything? Because we just want a onto map from B to A. We just want the onto map from B. Okay, so actually from this part is already onto, right? But you need to, but this part here doesn't tell you where you sense the other B, which is not approachable by that. So I just send it to something else. I just complete the definition of a function. Okay, we already have onto-ness already with fx. Okay, so then G is clearly onto. Okay, so we are done. Right. So this result here actually not very, not very interesting, but the proof itself is quite illuminating. Okay, the proof itself is quite illuminating. So how you construct one-to-one map, okay, how you construct onto map. Okay, this is the part that you need to learn. Yeah. Yeah. Huh? If and only if. Let me think. No, that one is by definition. This is definition. We actually define by this, but when we talk about it, it's like we really think about less thing because you can think about it. Because okay, first we define as injection to a smaller thing, but as a result is equivalent to what we interpret. Does it make sense? Okay. Does it make sense? Definition is using injection. That one is definition, no need to prove. This is what I said. Definition. So in our mind, what is less than? It's not 2 pencil is more than 1 pencil. Not like that. It's I can put an injection. I can put this 1 pencil into the one of the 2 pencil. You get what I mean or not? This is the definition of less than or equal. It's not the like which one is more. No. You get what I mean? You get what I mean or not? So now you need to change your mindset about less than. Is you can inject the fewer elements into a larger element set. Does it make sense? It's not like 2 minus 1 because 1 is greater than 0, so 2 is greater than 1. No, it's the injection. We talk about map, huh? Talk about map. Does it make sense? Okay. Less than or equal. The notion of less than or equal now is about injective map. Yeah. Does it make sense? Injective map, huh? Because in the usual order, how do you think about 1 less than 2? Surely you will say 1 less than 2 because 2 minus 1 is greater than 1. Because you have one more thing than me. 2 greater than 1. But now it's not this case. The case is this 1 here can be injected to one of the 2 things. Okay, it's understand as a map, not a number.
So as by injecting to n that is subset of t, it's not direct T, right?
Yes.
That's why it's defined as that way. Right?
Yes. Okay, so less than now become an injection, and not difference. Okay, before I give you a very broad idea, I want to prove you one more thing about this injection here. Okay, since you are a bit confused with less than or injection, right? I'll use more injection phrase here. So let's take 3 cardinal numbers. Then what? Then, of course, there's an injection from A to A. Okay. A bit like reflexivity, huh? Okay. Second is what we call a Schroeder-Bernstein theorem. Why there's a name towards this theorem, meaning this thing is very hard to prove. So that's why there's a name there. So what's this statement here? So if you can inject A to B, and you can inject B to A, then actually the two cardinality is the same. Okay, so maybe you think that this is quite obvious, but it's quite hard to prove. So that's why there's a name attached there, and then it becomes a theorem. Okay, bye. You tomorrow next. When? When's your calendar? Wednesday. Wednesday. Okay. Wednesday, Thursday. Okay. And then what else? If you can inject A to B, and you can inject B to C, you can inject from A all the way to C. So transitivity. Okay. And then so either you can inject A to B, or you can inject B to A. So one of them you can do. Even any two set. Quite obvious. Quite obvious. But okay, so let's see. So which one you think is easy to prove? Tell me. Which of them is easy to prove? Okay, I already tell you two is hard already, but what are easy to prove? 1 and 3 is obvious. Okay, let's talk about 1 and 3 first. Later we talk about 4. So 1 is obvious how? Same to resolve the identity map is the injection. 3 then? You just compose the two injection. So composition of two 1-to-1 map is 1-to-1. You can prove that. If you can prove it, then you prove 3. So I would say that 1 and 3 is obvious. If it's not obvious for you, please write it down. Okay, 2 is the hardest one. So let's talk about 4 first. Okay, talk about 4. 4 how? Yeah. 4. So either you have a map from injective map from A to B, or you have an injective map from B to A. Surprisingly, this thing needs axiom of choice. so why does it need an axiom of choice? So let's prove this. I'm not sure there's another way or not, but this way need axiom of choice. So let's look at this set of function. Okay, so what's this function here? So we're considering injection from U to V, where U is a subset of A and V is a subset of B. Okay. So you can check that this actually form a chain. Okay, you can check that this form a partially ordered set. So it will follows from John's lemma that this guy contains a maximal element. So I'll give you the argument here, then you will see what kind of chain you will expect from this F. So what this maximal element do? Okay, so either this maximal element is a 1-to-1 function from A to B, or its inverse is a 1-to-1 function from B into A. Okay, so you can see that what happened is this chain here will grow. Okay, either this U will achieve A first, or this V will achieve B first. Okay, John's lemma will give you this maximal element. Okay, depend on the A, B you start with. Okay. Does that make sense? Yeah, I only consider 1-to-1 map at first, not arbitrary F. It's a 1-to-1 map first. And then to achieve maximal, either I can achieve V equals to B or U equals to A, or both of them will equal AB respectively. Then I will get my 1-to-1 map. anywhere. Okay. Make sense? Okay. Does it make sense? Anything will work. Oh, you mean maximum? Let me think. What are you trying to say? You mean the maximum element must achieve A or B? I think that maximum element should be that, right? Maybe that is the definition of maximum element in the set. The maximum element, I think, have to do that. Because it's bounded above by B, right, or A. This chain. I mean the chain of subset. Chain of subset of A and B. Okay. Yeah, I mean, you can write out a more careful argument saying why this set is a partially ordered set. Yeah.
A to B, where V is the way apply close the way.
Why? Because U can equal to A. Right. Actually, what? Actually, it's in the set. Yes. So now I think you need to argue why the maximum element is what is giving you this. So I think you need to check. Yeah. So you need to check why the maximum element of this partial order set is exactly what I claim here. This is what you need to check. Yeah. Yeah. Try check that. But to check that, you need to give the partial order of this. Yeah. But this claim is like this. Yeah, but the idea is what I said just now. Yeah. Either you achieve, so either the chain achieve maximum when U equals to A first, or you achieve V equals to B first, or they achieve at the same time U and V equals to A. Okay. Yes.
Why is it's not?
Oh, why the set is not empty? Oh, why is the set not empty? Oh, very good question. I think you need to argue differently, right? Maybe you need to argue empty, non-empty, empty, empty, not empty, not empty. Correct. You need to argue, I mean, all the cases, no? Between two U, A and B, right? So you need to argue empty, 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 non-empty, non-empty, empty should be the same, and then non-empty, non-empty. So let's talk about non-empty, non-empty first. So non-empty, non-empty, in that case, the subset I pick here could be just one element set from two. Then this from one element set from A, one element set from B, then there's a injection there. So it's not empty. And then you keep building up this thing. So you keep adding in element. Makes sense? If it's empty, then if one of them is empty or both of them is empty, then I think you can straight away argue the statement we have just now. But yeah. But if it's not empty, then you use this. Okay. Does it make sense? Yeah. Okay. If you like, try and write in detail what's the partial order here, and then why the maximum element is exactly what I claim here. Okay. Yeah. So what's the maximum element of that partial order set? Okay, what time is it? 3:06. 3:06. Do you want to torture your brain or not? Should we keep the Schroeder-Bernstein theorem to next time? Keep to next time? Okay, maybe we can keep it to next time. In that case, let me see, what should we do? Okay, how about we keep the Bernstein theorem to next time, and I post the proof out. You can read it first, okay? Then next time I explain the proof. There's a construction about this proof, the Schroeder-Bernstein theorem. Okay, so now we assume that this is true, huh? It is anti-symmetric, okay? So it's anti-symmetric, we assume. We haven't proved it, so we assume. Okay, I pause the note and then we will discuss next time. And corollary, there's a nice corollary here. Okay, so we have a similar law, which is the trichotomy law. Trichotomy law on this cardinal number. So the cardinal of A is strictly less than B or equals to B, or B is less than A. Okay. Is it clear? Clear now? Just now we have either less than equals to or greater or equal to, right? So if it is equal, then we are done. If it is not equal, then it must be one of this. But if it is one of them, it is not equal, then it is strictly less than or strictly greater to. All right, so we have this trichotomy law. So when's the first time you see trichotomy law? Don't know. Huh? Never see before. Never see. Never see. Oh, okay. So I was teaching MA1 this semester, right? So I introduced them a few axioms about real numbers. So what's a real numbers? Real numbers is a complete ordered field. Okay, you can prove that any two complete ordered field are field isomorphic. You guys understand field isomorphism? Isomorphic as a field. Okay. So in this order axiom, right, you have trichotomy law. So any two number, there are only three possibilities. Okay, either A less than B, A equals to B, or A greater than. Sorry, am I saying the right thing? A less than B, A equal to B, or A greater than B. Okay, three things. Three things can happen. Okay, one of the things must happen. Okay, between two numbers. So this is called the trichotomy law. So here we also have trichotomy law for cardinal number here. Okay, so you see, this cardinal number really, how to say, really resemble natural number. Really resemble natural number here. I mean, maybe we don't talk about DR and CR. Let's talk about just finite set case. They resemble numbers. This finite set resemble numbers. How to get number from this set here? We take the cardinality. So you give me a finite set, I take cardinality of the set, I will get a natural number. And then this cardinality will satisfy similar property of natural number. Okay. So let me do some detour here. You don't need to copy it. I want to introduce you some very advanced knowledge here. So let's do some detour here. So what I want to say is a finite set category 5. Here. Category 5 natural number. Okay. So what do I mean here? So I want to define the category of a finite set. So I don't want to tell you all the axiom, but what I want to tell you is what is inside this category. Okay. So the category of finite set is defined by two data. Okay. So one data is objects. I need to tell you what's inside there. So it's a category of finite set. So in particular, the things here are finite set with finite cardinality. And the morphism here is the function of set. Okay, so I just need to tell you two data to specify a category. And what is the construction we have just now? We have a finite set from this category, okay? And to the finite set, we can attach a natural number to it, which is the cardinality, okay? What am I doing is I'm lifting, okay? I'm lifting the structure of n to the category of finite set here. For example, what? For example, in natural number, what can you do? You can compare two natural number. For example, 1 less than 2 here. But if I leave it to the world of category of finite set, what does 1 and 2 represent here? These are represented by the singleton and the set of two elements here. Okay. And we said that there's an injection from singleton to two set with two elements. But you see, 1 less than 2 is just one data. Here, how many data you could have? You could have more than one data here. It could be two types of injection here. You know? So this inequality here is not just realized by one injection. It could be realized by different injection. So there's more thing we can do in category of finite set than you can do in the normal arithmetic work. But everything happens here. But we can do more things in the category of set because you see, we can have different injection. Right? So this is why we go for category theory. Okay? We try to categorify all the simple concept in mathematics. Yeah. In particular, because Gary and Youngin, right? Because they took FYP with me. So we look at the Jones polynomial, right? Polynomial. We can even categorify polynomials. But we are not using set anymore. Maybe we use vector spaces. Categorify. Even more structure. Yeah.
Size.
The size of category. We don't do that because these objects, right? They so in the category we have like small category. So small category means like objects from a set. Actually, in category we don't require this object from a set. It could be just some random collection. Maybe yes. I think so, yeah. Either is a set, is a non-set, yeah. But we don't really care about whether it's a set or not, yeah. What we want to leave, right, is the structure. That is the structure. Because it's the interesting choice we can make here. We can send x1 to s1, or we can send s1 to s2. And then these two things is different map already. And then different map can do different stuff. But here, just two greater than one. That's all. Yeah, so this is a detour. All right, so let me see. Okay, two more things. We go to continuum hypothesis, and then we'll end this course. End this lecture. End this course. Okay. Let R infinity denote the set of all infinite sequences. Okay. I don't want to look at R2, R3, R4, Rn. we will use the same method to prove here. So let's straight away look at infinity of R. So what is R infinity? So these are the infinite sequence. Okay, then the claim is, you want to guess how big is this R infinity is? How big is this? Yes, how big is this? C. Yeah, just as big as R. Okay. Yeah, so how to show this? We can use the Bernstein's theorem. So prove that there's an injection from R infinity to R and then from R to R infinity. Then you can have the result. Okay, so let's do it. So how are we gonna do it? So instead of proving it to all right. Okay, so what we're gonna do is let me think. So we will associate it to the open interval 0 and 1. Okay. Recall that this is true. Okay. And we don't really want to look at so many things in R infinity. Instead, we just look at the ball. Okay, what is this ball here? So I specify the size of x1 to s infinity. So what is this Si here? Si here, I just want to restrict them from 0 to 1. So in this case here, instead of looking at R infinity, we just look at B is enough. Okay. I make the size smaller a bit, but I still have the same number of elements. Okay. So it suffices to show the cardinal of B is C. All right. So how are we gonna do this? I think one direction is easy, right? Which injection is easier? Yes. So we take 0, 1, 2. So what can I do here? What kind of injection I can make? Let's go to 0 is not in my B. 0 is not my B. Okay, unless you change the interval, change the bijection, you cannot. But what we can do is we just make a constant sequence, no? Right? To make a constant sequence. Okay, yeah. So if you want to make S0, 0, 0, 0, right? Make sure your B got 0 inside there. If you want to make sure the B got 0, then maybe you need to change this bijection. But last time we showed that whether it's closed, open, or equivalent to 1. Okay, so one direction is easy. So this one is easy. So not that. This is a injection. So far so good. Okay. So we get what? So we get one inequality already. So B is at least greater or equal to C. Okay. Then we need to define another injection. So we need to find another injection from B back to 0, 1. Okay, so how, yeah? So, I mean, what to do? So, what is inside B? Yeah? How do we write the things inside B? B is a infinite sequence, okay, such that every term is bounded between 0 and 1. So how do I produce a number in 0, 1? So each of these is what? Decimal representation. So how do you build one number inside 0. Zero, I mean bounded by 0 and 1. Diagonal. Diagonal?
0.
Okay, so let's write down. So by decimal expansion, we can write x1 equals to 0.x11, x12, x13, so on, right? x2, right? Similarly, we can write x21, x22, x23, so on, right? x3, we can write x31, x32, x33. So now the problem is how we define fx. So which number I'm going to send to 0. What? Sorry? Power series expansion? What? This is number. Power series expansion is function for function, right? Yeah. Yeah, so we just run through all the digit like what we did for the rational case. Or maybe something like this. Okay, so we just write 0.x11, x21. For example, this is just one example. You can pick other example like what we discussed last time. Okay. Yeah. Sorry?
Like just now you say one number.
Yes, so you need to fix that as well. Yeah. Whenever you want to do decimal expansion, right? Make sure you fix convention. Okay? You want to fix ending. You want to avoid ending by 9 or you want to avoid ending by 0. Fix one. Right? Yeah, you need to put that technicality in. Okay, so this is also an injection. You need to prove that this is the injection. Okay, so I'll prove that this is an injection. Is it clear or not? This is the injection. Is it clear? Yeah, no. If two image is the same, they should come from a same set of x1 to x infinity. Is it clear? Because our order here is actually a bijection, right? So you can take this, reconstruct your sequence. And then you can compare your sequence. Okay. Which is an injection from B to 0, 1. Okay. So then we are done because we already have the Cardinal of V is less than equal to C. Okay. Then by Schroeder-Bernstein theorem, it is equal to C. So yeah. Question. Yes.
S1. S1.
You mean S1, S2, S3? Okay, the problem with that is because you are like putting infinity in between the sequence. We don't want to do that. We want to build one sequence only. So it's like I have a way to like specify what is in between. You get what I mean? Okay, let me write down what is this what you mean? Are you saying that you want to do like 0.x11, x12, x13, x21, x22, x23? Is this what you say? Yeah, right. Okay. So we want to avoid this kind of thing. You see, sequence inside a sequence. Yeah, we just want to produce one sequence. This is a bit hard to. Why is this a number? I mean, for sequence, right? We only know that the thing. How to say, huh? How to say it? What I want to say is this is not well defined. This item is not well defined. Because where do you attach this? This one haven't end on. Then you cannot attach x to 1. Never end. Never end. Yeah, never end. So when do you attach x to 1? Huh? Don't know where to attach it. Yeah, not well defined. Okay, but here, okay, because we attach to what we have before. But also we already attach everything because this pattern will cover everything. The pattern we produce will cover every term inside the sequence. Does it make sense? Okay. Yeah. So doing this is not well defined because you don't know where to attach the second set of a sequence because first sequence haven't finished yet. So similarly, you can prove R2 is equal to C, R3 is equal to C, and so on. Okay. And then to lead to this continuum axiom, we have last theorem here. It is if A is any set, then the cardinality of A is strictly less than the power set of A. This is how you discover that something bigger than real number, for example. So, I mean, one direction is easier. I mean, not one direction. I mean, why is it less than equal to is easy because you can have an injection. So, just quickly run through it. So, A to the set containing A is a one-to-one map. So, this implies that the cardinality of A is less than or equal to the cardinality of power set of A. Okay. Why is it not equal? Why is it not equal? Right? It's very interesting. We come back to the Russell paradox again. Okay, so how do we prove that A is not equal to B? Sorry, A is not equal to the cardinality of PA. So suppose, okay, suppose I have a map from A to power set of A. Okay, then we can construct a set which is everything in A such that A is not in FA. Does it make sense? Because FA now is a set. Because power set is a subset of A. So you can talk about A inside or not inside FA. Okay. So what? Then in particular, this guy, right, is inside the power set of A because you just pick something from A. Okay. So suppose you can reach X by sum B. Okay. Suppose you can reach this set. What does it mean? Suppose you can reach this set by sum B. Wait, step by step. Okay, so either B is in X. Okay, one possibility is B is in X. If B is in X, means what? B is not in FB. Contradiction. Can anyone see the contradiction? Contradict what? Because X equals to FB. Okay, maybe if you say there's a B, right? Maybe B is not in X. No? If B is not in X, means what? Then B is in FB again, but FB is still X. Another contradiction. So you cannot reach this set. In particular, this subset you cannot reach by this F. Any F you give me, I construct one thing that you cannot reach one. Okay, that means there's more thing inside the power set. So thus means what? X is not in the range of X, F. Meaning F cannot be onto. Any F cannot be onto. I construct an X that you cannot reach. Okay, so done. So now finally the question is, I don't want to copy again. So if there is there a cardinal number between C and D? Or you can ask, is there an infinite set A in R with no one-to-one map from A to N and no one-to-one map from A to R. And so this proposed question is, a proposed answer is continuum hypothesis. So there's nothing like that. Okay. And you can generalize this continuum hypothesis to say that there's no cardinality between A and power set of A. Because in the assignment, you will prove that power set of N is C. So you go from D to C. So there's nothing between D and C. So generalize it. There's nothing between cardinality of A and the cardinal power set of A. So I mean, you can try and prove or what? Because I think they state that this CH, right, is independent with axiom of choice. I saw a claim is the general continuum hypothesis will imply axiom of choice. But CH has nothing to do with axiom of choice. This is some foundation question from set theory. Okay. Yeah, can try and think about it. Yeah, any question before we break? I think we are on time, thanks to the extension of 1 hour. Last time half hour, this time half hour, so we are on track. Yeah, right. So try and think about it, and we can discuss if you like. And because discussing this foundational problem, right, most probably can build new field, because you need to build new tool to solve it. If you cannot solve it all tool, this is what? This is another theorem, right? Gödel incompleteness theorem. Gödel incompleteness theorem says what? Every set of axiom, you can construct a statement that you cannot prove using the axiom. So you need extra stuff to prove it. So that's why we will, like in mathematics, we will find approach from different field. Okay. Yeah. Okay. Yeah, that's all from me today. And then you can come to my office hour if you have problem on assignment, tutorial, or what. And please make appointment to me so that I know you are coming. And I'll see you on Wednesday. Hey, where's Pet Hong again? Pet Hong disappear again. Hello? Huh? Didn't turn up. Turn off. Okay, never mind. We'll let AA settle. What do you mean by 6 classes?